All right, welcome back. Today we are going to continue our discussion of metabolism, and we are going to be moving into the citric acid cycle. So here, learning objective, summarize the reactions of the citric acid cycle. So going back to our overall pathway, what we're going to focus in on now is once you have pyruvate, which is the outfall from glycolysis, what do you do with it? And how does that ultimately end up as CO2? And this is a two-step process um, involving turning pyruvate into acetyl-CoA and then feeding that acetyl-CoA into the citric acid cycle, which is a multi-step process in and of itself. All right, so the first step here is we have this compound pyruvate, and we are going to turn it into something that we call acetyl-CoA, right? So this CoA actually stands for coenzyme A, and coenzyme A is actually this large functional group here. Notice that on one side, we do in fact have ATP serving as, again, a handle, okay? So here we have the adenine ring, we have the ribose backbone, we have a couple of phosphates, and then we have this functional group attached onto the end. This is actually the synthesis of a couple of amino acids. I'm sure if you look at them closely, you can recognize them. But ending here, we have this thiol functional group. I'm sorry about that, didn't mean to move. The thiol functional group is where we are essentially going to add on an acetyl group. And an acetyl group is simply a carbonyl carbon with its oxygen and a methyl group attached onto that. So that is together called an acetyl group. That is, of course, a 2-carbon compound, and pyruvate is a 3-carbon compound. So we are, by necessity, going to lose one of those carbons as carbon dioxide. To achieve this, we are also going to steal electrons, and we'll be utilizing NAD to do that. Again, if we utilize NAD, we steal both a hydrogen and its electrons that are involved in the covalent bond to its parent carbon. That will leave a hole that allows us to attach the coenzyme A molecule. So the reason why we utilize this coenzyme A is that this, what we call a thiol ester group, is actually a very energy-rich compound. And I'll give you more detail here in a moment. But if we break it down, again, this coenzyme A into its various parts, here again we have the ATP part, here we have something called pantothenic acid, and here we have beta-mercaptoethylamine, which is actually an amino acid derivative, as is this here as well. So the reason why this thing that we call thiol ester is so powerful is if you think about a general oxygen ester, where we have a carbonyl carbon attached to an oxygen. That double bond on the carbonyl is, those electrons aren't always there, so there is a resonance structure where the double bond is sometimes over here, right? And so it gets this kind of fusion compound, or this synthesis of two various things. Now, the bond holding this carbon to this oxygen since we are dealing with a carbon fighting with two oxygen molecules, which have the same electronegativity over these electrons, this has a certain amount of negative delta G, or free energy, stored in it. But if we look at the thiol ester version of this, the same thing happens with sulfur in that we have this resonance structure where the electrons can form over here, but it's not quite as powerful as we see here, right? And that is because although sulfur has the same valence electrons as oxygen, it is bigger and those electrons are further away from the nucleus and are held less strong. So consequently, it is inherently less electronegative. That means that there is more energy available through the lysis of this bond, right? So if we take this, an oxygen ester, and lyse it, we get a certain amount of energy. If we take a thiol ester, there is inherently going to be more energy. All right, so now that we have acetyl-CoA, what do we do with it? Okay, and here I'm going to go through this cycle in a couple of different ways, looking at some key features differently at different points. So here we are going to take a 2-carbon compound coming in as acetyl-CoA, and we are going to combine it with oxaloacetate, which is a 4-carbon compound. That is going to yield citrate, which is a 6-carbon compound. Okay, so this plus this equals this. Now, once we have citrate, what we are going to do is dehydrate it, okay? That is going to result in the creation of a double bond. That double bond then becomes a reactive point where we can rehydrolyze it. And this is essentially accomplishing a slight structural rearrangement, okay? So here we used to have this alcohol group here. By introducing a double bond and kicking that group out, we can now put the water back on, but in a slightly different position, okay? That primes this compound to feed into a reaction where we can steal a couple of electrons away. And again, remember, NAD is stealing 2 electrons with a proton or a hydrogen atom, whichever way you want to call it. But it is taking both, and in this case, it is going to steal it in such a way that we liberate CO2. Now remember that carboxylic acid is essentially just a whisper away from being CO2, right? So these are groups that really kind of want to leave. All right, so once we've achieved that, we now have alpha ketoglutarate. That compound can essentially go through the same type of reaction where we bring in NAD, we steal 2 electrons with its hydrogen off of one of these carbons. That is going to result in CO2 leaving, and we're going to utilize this to again bring in a CoA molecule to achieve this right here, which is succinyl-CoA. So this is occurring on a different enzyme than what is happening up here. It just so happens that they are both utilizing the same coenzyme group to achieve its end. Remember, coenzymes are just simply functional groups that are attached to enzymes or utilized because they can do something that the amino acids can't do on their own. Okay. Now, once we have this compound here, we can use a substrate level phosphorylation technique in order to utilize the energy stored in the silyl ester bond to facilitate the phosphorylation of GDP to GTP. In this case, GTP is an equivalent to ATP. It's easy to switch back and forth. It just so happens to utilize GTP in this case. And there's actually a couple different versions of the enzyme that carry this out. Some of them actually use ATP. So this can happen in a couple different ways. The resulting compound here is something that we call succinate. The succinate compound is then stripped of a couple more electrons. This time, however, we are going to use something that we haven't seen before, and this is a compound that we call FAD. This is another example of a coenzyme molecule like NAD that it can capture electrons, but it's slightly different in structure. So let's stop and examine that briefly. So the key part of FAD is this flavin ring structure here, right? And this is built from riboflavin, and you might recognize that as one of the B vitamins. And the key part of it is in this ring here, we have these two carbons that have double bonds to nitrogens within these rings. This is the business end of this molecule. Now, we can take this and sometimes we will attach it directly to a protein through a phospholinkage. Other times we will attach it onto our ATP handle and it will be something that is attached to a protein. So whether it's covalently linked or attached through ATP binding site, it doesn't make a difference. It will still work the same. The key thing that's different about this flavin ring is it still carries up to 2 electrons and a proton, but it actually has the ability to gain and lose those electrons one at a time. Okay, this is going to be important when we talk about the electron transport chain and how we pass off electrons onto that system. Okay, so that is the real key reason why FAD is used in this case rather than NAD, and this will make more sense when we talk about where this reaction is actually occurring, which is in the electron transport chain. So coming back to this idea here, we've utilized that. That is stealing a couple electrons, which is going to yield this compound here. We can then hydrolyze it to malate and steal yet a couple more electrons to leave us with oxaloacetate, which, if you remember, is one of the starting compounds, hence closing the cycle. Okay. Now, I want to take a look at this in a slightly different way. And when we look at it, we're going to look at it for where the carbons come in and where carbons leave. And we'll pick this up in part 2.